Okay. How was Friday? Yeah. Okay. Anyways, do you want me to go over anything? You want me to give you a crash course in this? Yeah? No? No? Yeah? Maybe? Okay, whatever. We will. So, pure water is not pure water. Okay? There's no such thing as pure water. Now, the reason why there's no such thing as pure water is because water can ionize itself. One water molecule reacts with another water molecule and they turn into not water. So there's no such thing as pure water. Now, we can make pure water by trying to get rid of everything else, but the water will react with itself and make some other stuff. Even pure water has a small amount of hydronium ions and hydroxide ions. How is this possible? I don't know. If there are no acids in water, how can we make hydronium? It turns out water can ionize itself, called the auto-ionization of water. So what has to happen? Water reacts with water to make hydronium and hydroxide. All you have to think about this is a proton gets transferred, hopefully, yeah, I can do it. Okay, a proton gets transferred from one water molecule to another, and then you get hydronium, H3O, and hydroxide. Okay? Now, let's think about this for a second. This happens a lot. This happens so much in water. Now, do you think this process of a proton being transferred from one water to another, is that going to happen more often or less often if we heat up this water? Do you think we're going to get more protons being transferred or less if we heat up the temperature of the water? More. Why? Yeah, there's a greater energy in the system. Also, you get more collisions between these molecules, and the more collisions you get, the higher potential there is for a reaction to take place. Okay. Now, this reaction has a K value. It's got an equilibrium constant. When I take a look at this reaction, okay, what would be the K value? If you were to look at this reaction, could you figure out the equilibrium constant expression for it? Is this homogeneous or heterogeneous? It's heterogeneous. So what do we ignore in a heterogeneous reaction? Liquids and solids, right? So the Kw, the K water, right, is products over reactants. But what number are we going to put in place of both of these reactants? The number 1. So this, right, this stuff divided by 1. Oh, okay. So there's nothing on the bottom. So the K value for this reaction is just the concentration of hydronium times the concentration of hydroxide. And this value, you don't have to memorize. This value is located in your data booklet. You don't have to bring up your data booklet. I can if you want me to. I think it's coming up on the other one, other monitor. Here we go. So when you look, you just skip past the periodic table on the first couple pages, skip past all of this incredibly useful information that if you don't use this information on the diploma exam, I will be sorely disappointed in you. And you keep going. And right here, for a table of miscellaneous whatever, right, down here, water ionization constant, or the dissociation constant for water. The value of Kw is 1 times 10 to the negative 14 at 25 degrees Celsius. Okay? So that value will always be given to you. You always have that available to you. Okay, no problem. So let's take a look at this. We've got a pH spectrum up on top. And does it make sense that if the pH is 0, then the pOH will be 14. Do you remember that from Chem 20? Yeah, okay. pH is a measure of how acidic is something. What's pOH? Yeah, it's a measure of how basic something is, right? It means, roughly speaking, what is the power of hydronium? What is the power of hydroxide? Now, power doesn't mean like power. It means like a mathematical something raised to the power of something. That's what power means, right? So, hydronium concentration decreases. You get less and less and less and less hydronium as the pH goes up. But remember, right? A pH of 0, if the power of hydrogen is 0, what's anything raised to the 0? 1. The concentration is 1, right? If the power of hydrogen is 1, then the concentration of hydronium will be 10 to the negative 1. That's the power, right? Do you see how the power stays the same as the pH the whole time? This is a mathematical relationship between these two things. So every pH unit decreases 10 times the concentration of hydronium, or increases 10 times the amount of hydroxide. So if my concentration of hydronium was 10 to the negative 1, 10 to the negative 1, what's the power on this hydronium concentration? Negative 1. So what would be the pH of this thing without doing any math? 1. Does that make sense? That's how this mathematical relationship works, right? That's a lot. 10 to the negative 1 is 0.1. That's a lot. Like in terms of chemical concentration, 0.1 mole per liter that's like actually quite concentrated compared to what we see in nature, okay? So the pH is increasing because the concentration is decreasing. At really low pHs, we've got tons and tons of hydronium and a little itty bitty amount of hydroxide, right? And as the pH increases, slowly we gain more hydroxide and we lose hydronium, okay? On the top and on the bottom, we've got concentrations of hydronium and concentrations of hydroxide. If you were to do this, if you were to take that times that, every single time you would end up with 10 to the negative 14. So that's just showing you that this equilibrium constant does hold true across all of these pHs. Okay, that's all we're saying. Okay, this is the real meat and potatoes of what we wanted to do on Friday. Did you write down everything? Did she write down everything on the board, or did she just put up these notes? She wrote them down. Okay, all right, perfect. So you were responsible for memorizing all of this information. And I know that sucks, but you should have memorized most of the stuff in Chem 20. And a lot of you took Chem 20 last semester or last year, right? I feel bad for the people who took it in second semester of grade 10, which is like well over, or not well over, but it was basically 2 years ago. If I want to go from hydrogen ion concentration or hydronium, right? Hydronium ion concentration, same thing. If I want to go from this to this, there's a very specific equation for that. If I want to go backwards, there's a very specific different equation for that. Now, for those of us who have taken Math 30-1, we should already kind of recognize this relationship, right? Logarithms and powers. There's a very specific relationship where if I took, right, the log of this thing, the pH will pop down, and I just need to stick a negative sign to cancel the negatives, right? So they're just rearranged versions of each other. Now there's acid equations and there's base equations. And what do you notice? What's the difference between the acid equations and the base equations? pH for acids, pOH for bases, hydronium for acids, hydroxide for base. Are they the exact same equation? Okay, so you don't have to memorize 6 different equations. you have to memorize basically two equations. One you probably already memorized because it's so dang easy, right? And the other one you can just naturally figure out yourself. You don't even have to memorize this. You can figure this out yourself if you wanted to. So really, I'm telling you right now, really all you have to do is memorize two equations and be able to turn them from acids into bases, right? Is that okay? We can go from anything on this chart to anywhere else on this chart, and it's a maximum of 2 steps in order to do that, okay? And then we did some reminders. This is just unit analysis. That's all this is. We went through some unit analysis. So if I dissolve 1.17 grams of hydrochloric acid in 1.45 liters of water, because HCl is a strong acid, all of my HCl turns into hydronium, right? So we assume they're the same concentration. That's what we have to assume, right? So we go, okay, what's the concentration of HCl? And then we do some unit analysis, okay? The chant that we will do, you're all, by the way, I don't know if you knew this, but you're all part of a cult right now. By being enrolled in my science class, in my chemistry 30 class, you're all part of a cult. I hope you're okay with that. You just deal with it, okay? Okay? Our cult, does anybody know what it is? What's the name of our cult? No? The name of our cult is Start With What You Want. Start With What You Want. Start with, no? Okay, wait. So when we're doing unit analysis, okay, the reason why we're making a cult is because when we make a cult, okay, that's so insane that you're going to remember it for the rest of your life, hopefully. So if you want to start unit analysis, you need to define what you're looking for at the beginning. That is the most important part of unit analysis. What are we looking for? If I wrote down this for you, right? I'll put up the screen shade. If I wrote down this for you, what unit do we want on top? Moles of hydrochloric acid. What unit do we want on the bottom? Liters of hydrochloric acid. Cancel out every other unit. Every other unit is useless to you, okay? The only 2 units that matter to you are moles of hydrochloric acid on top and liters of hydrochloric acid on the bottom, okay? That's the way we would do this. So if I want moles of hydrochloric acid on top, okay, and we're being given, holy guacamole, are we given moles anywhere in this question? Do you see moles in here? No. Okay, so just give up, right? Yep. Wow, it's very sad how quickly you gave up on Monday morning. I don't see moles, but I see something related to moles. What do you see that's related to moles? Moles and mass are related to each other. How are moles and mass related to each other? Molar mass, right? Okay. The function of the molar mass is to convert between moles and mass. That's why we call it the molar mass. So if you're given mass and you want moles, just use the molar mass. Okay, perfect. So we're going to start with molar mass. 1 mole of hydrochloric acid per 36.46 grams of hydrochloric acid, right? Do we have moles of hydrochloric acid on top? Woo! We're halfway there. Come on, let's go. So we got moles on top and we got grams on the bottom. Do you like grams on the bottom? No, then cancel it out with grams on the bottom. Sorry, grams on top. Okay, cancel it out with grams on top. So grams and grams cancel. You're left with moles. That's the only unit you have right now. So you're left with moles of hydrochloric acid. Are we done? No, you don't want moles. You don't care about moles unless it asks you for moles, right? But in this case, you don't want moles. You want moles per liter. So the only thing you have to do is stick liters in the bottom. You just do it, right? So then you will get your appropriate concentration. Now, I'm not going to go through every single example here, but that's how unit analysis works. What's the most important part of unit analysis? The very beginning. If you don't know what unit you're looking for, if you've got no clue what unit you're looking for, you are dead in the water. You cannot do unit analysis unless you know what unit you're looking for, okay? How many people have memorized that concentration is in moles per liter? How many people have memorized that? Okay, did you have to?
No.
No, okay? When you look at this thing, right? The reason why this thing is so important is because it defines every single unit that you're going to be using this semester, okay? Let's look here for concentration. I see amount concentration. What's the unit, what's the letter we use for amount concentration? C. So that's why I always write C, concentration measured in moles per liter. And it tells you it's measured in moles per liter, okay? What if I said a unit that you've probably never heard before in your entire life? What about the specific heat capacity? Can you find specific heat capacity anywhere on here? Yeah. So what units are they in? Joules over grams degrees Celsius. Those are the units. If you want to solve for specific heat capacity, those are the units you're looking for. You could do a question right now without me teaching you anything. You could do a question and solve for joules per gram degree Celsius because you're all destroyers of unit analysis, okay? Or you will be in a couple months. So anyways, I'm not going to go through all that because the notes are online. You can work through it. Also, most of this is a review of Chem 20. So, all strong acids 100% turn into hydronium. All strong bases, every single strong base is an ionic hydroxide, and we assume it completely dissociates, okay? So what I have, I just want to do an example on the board, because this is going to be way quicker than like reviewing information or anything like that, okay? What is the pH of a 0.0127 mole per liter solution of calcium hydroxide? Now let's look at this. Let's try and look at some important pieces of information in here. What is the pH? Do you know how to get pH? What are the only ways you know how to get pH? What? Negative log of the hydronium concentration. So either we're going to need hydronium concentration or what else? Yeah, not hydroxide, but we can get pH from POH, right? So one of those two. As long as we can get one of those two, then we're golden. Then we can turn it into pH. Okay, of 0.0127, nobody cares what the number is, mole per liter solution of what? Calcium hydroxide. What should you immediately notice about calcium hydroxide? It's a blank base. It's a what? It's a strong base. Why? How do you know it's a strong base?
Calcium's group 1.
It's calcium's group 2. Okay. But it's an ionic hydroxide. Right? You just have to assume that this will dissociate 100%. So calcium hydroxide will turn into calcium ions and hydroxide ions, right? Right? Right?
Yes.
Right?
Absolutely.
Oh, I boned up, didn't I? This is incredibly wrong. Give me reasons. Give me reasons why this is so wrong that I should be whipped in the town square right now. Yeah. Which law are we not following right now? Both of them, right? The law of conservation of mass and the law of conservation of charge are not being followed in this chemical reaction. Immediately you should know, oh, I messed up. Uh-oh, I messed up big time and Walton's going to not do anything at all. He's going to mark me wrong, but whatever. Okay? So 1 calcium, 2 hydroxides, 2 hydroxides. That fixes all of our problems, right? Okay, no problem. Jaden.
Shouldn't calcium hydroxide in the equation aqueous, or like in the question, so shouldn't it be aqueous with your reactant?
Yeah, sure. Doesn't change any of the real honest-to-goodness chemistry, but yeah, I agree. I'm basically saying that I'm starting with an aqueous solution, but I could have just as easily started with a solid and dissolved it. But you're right. So we've got calcium hydroxide turning into calcium and hydroxide, and what do you know is the concentration of calcium hydroxide? So 0.0127 mole per liter. Okay, nobody cares what that number actually is, but what do you notice? What's the only thing in this equation we really care about?
Hydroxide.
Can you understand why we care about hydroxide and nothing else here? Why?
We wanted to get pH.
Good. So we want to turn this into this. Now, without really doing any math, what do you have to do? Without really truly doing any chemistry or anything like that. Like if one of these makes two of these, then 0.0127 of these will make double that. Does that make sense? Okay, you don't have to even show that to me because that should be so simple that whatever. So that's 0.0254 moles per liter. So that's my concentration of hydroxide. So if my concentration of hydroxide equals 0.0254 moles per liter, then we can get pOH super easily. Do you agree? Negative log 0.0254 moles per liter. So go ahead, prove to me that you can do this calculation on your calculator. You're going to get a pOH of, I don't know, 1.8 or something. 1.59. Give me a buttload of digits. 5951 6628 blah 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 blah. Okay? So that's our pOH. That's awesome. Are we done the question? No. What do we want? pH. Is that an easy calculation? 14 minus this, right? So our pH is going to be 12.40483371 blah 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 blah. Now, I can't drag this up, so you're just going to have to peek over beside somebody's head. Is that our answer? No. This is something that my Chem 20s last semester had so much trouble with. Okay? How many significant digits are in the original information from the question? 3. That means we need 3 significant digits in our answer. I'm going to give you 10 seconds to write down anywhere. Write it down and prove to yourself that you can write this number to 3 significant digits. Don't say anything out loud. Don't even talk to your partner. Don't even ask them. Don't consult them. Just write it down. I'm going to circle the first 3 significant digits that I see in this number, okay? You ready? I circled the first 3 significant digits that I saw in that number. Do you remember that rule? Kind of? Sort of? Not really? It's okay if you don't remember. That's fine. I'm not trying to shame you right now. When you're talking about a pH, the number out in front does not matter. Okay? And if you don't believe me, I can prove it to you, but I don't have time to prove it to you right now. Prove it to you at lunch or at Flex or something like that. We don't got time. Ain't nobody got time for that. Okay. So, what is this number rounded to 3 significant digits? 12.405. 12.405. Is that okay? Is that okay? Is that okay? All right. Perfect. So then we went through some stuff and we just did a bunch of calculations. That's all. It was just a bunch of calculations. That's all we did. Okay. I'm not going to go over the rest of this stuff, but we will get used to these pH calculations as we go. Okay. I will let you know a question similar to this. A question very similar to this will appear on your quiz on Wednesday. So this question is on video. It's going to go up on YouTube later on. The notes are on PowerSchool or Google Classroom or whatever, okay? So let me know if you have any questions. But yeah, we are going to have a quiz on Wednesday about 16.1, 16.2. Now, can I get you to